Hello and welcome back to Aviation Map Reading. This is part 2 and I'm Conway Bound from Independent Productions and Aviation Services. In this part we're going to talk about coordinate systems, map legend and marginalia, the concept of north and map interpretation and navigation. First, a quick review on what we covered in part 1. Well, what is a map? Well, a map is a representation of the Earth's surface, as we said. A topographical map, or a topo map, is a map where topographical data is the most important factor on the map. A chart, as we saw in part 1, is a map that's primarily used for navigation, and a cadastral map is a map with property detail. Let's have a look at a visual navigational chart used for aeronautical navigation. Here is the 1 to 500,000 VNC, visual navigational chart, and compare that with the following. A topographical map. You can see the difference there in the amount of information is presented to the person with the map. Alright, let's get on with coordinates. We'll start off with latitude and longitude. What's latitude? Well, a latitude is a measurement of angular distance north or south of the 0 degree line, which is the equator. They are parallel with each other, and they become smaller in circumference as they go closer towards the poles. Longitude, on the other hand, is a measurement of angular distance east or west of 0 degrees, which is known as the prime meridian, and that passes through Greenwich and London. The system that we use in latitude and longitude is a sexagesimal system, which is a base 60 system. What that means is that the entire world is divided up into 360 degrees, which is a multiple of 60. And those 360 degrees are each divided into 60 minutes, which again are each divided into 60 seconds. Let's have a look at an example of that. As you can see here, the 0 degree line is the equator. And so when we talk about latitude, these are the latitude lines that run east-west. They are parallel with each other. But as you get closer and closer to the poles, they become smaller in circumference. So you can't use those for measuring scale. On the other hand, the longitudinal lines, these ones that run north-south, they are all the same circumference around the Earth's surface. However, they're not parallel to each other. They converge at the poles. But because they're all the same size, we can use those for scale. So this longitude line here, this meridian of longitude, is 90 degrees west, and this one here is 80 degrees west and 70 degrees west, etc. With the parallels of latitude, this line is 10 degrees south, 20 degrees south, and in the northern hemisphere that would be 10 degrees north and 20 degrees north. These red lines are the various tropics, the Tropic of Cancer to the north and the Tropic of Capricorn to the south. Anything contained within these lines is called tropical. Here is another image of the same concept. As you can see, here's that prime meridian passing through London, down through Western Africa. Any meridian to the east of that is suffixed by the letter E. It's called east, 30 degrees east, 60 degrees east, 90 degrees east. And conversely, heading west, it's 30 degrees west, 60 degrees west, etc. And they meet on the other side of the globe at the 180 degree line, which is where the international date line is, but we'll talk about that in another part. So when we talk about using latitude and longitude, an interesting point to note, and one that's very useful for navigation, is that 1 minute of a meridian of longitude, so that's 1 minute measured on the north-south line, the longitude line, is equal to 1 nautical mile. And 1 nautical mile is 1.852 kilometers, 1800 meters roughly. Therefore, 1 second, which is 1/60th of a minute, would be approximately equal to 30 meters. So 1/60th of 1,852 meters, or 1.852 kilometers. How do we write latitude and longitude? Well, by convention, latitude and longitude is shown as degrees in whole numbers, minutes and in whole numbers and decimals, and we discard the seconds. Let's have a look at some displays of that. So if we're going to write a latitude and longitude, thus 31 degrees, 53 minutes, 28 seconds south, 152 degrees, 30 minutes, 32 seconds east. Now note this, there are 360 degrees in a circle. However, because we are looking at north and south here, and we only go from the equator to the North Pole or the South Pole, that can only ever be 90 degrees, because that's 1/4 of 360. I'll show you that on the picture later on. And remember what I said before about the longitude? It goes from 0 degree prime meridian around to 180 degrees on the other side of the world, which is in the middle of the Pacific. So this number will never be any greater than 180. These numbers here, these minute numbers, well, there are 60 minutes to each degree. So this is 31 degrees and 53 sixtieths of a degree, 53 minutes. And then this number here is 1/60th of this number. So that would be 53 minutes and 28 sixtieths of a minute, or 28 seconds. Because 28 is very close to 30 and 30 is half of 60, if we were to decimalize this, it would be roughly 0.5, because 28 over 60 is roughly 0.5. The same over here, 32 over 60 is roughly 0.5. And because we use decimals, this is how it would look. 31 degrees, 53.5, which is close enough to 53 minutes, 28 seconds. And 30.5, which is close enough to 30 minutes, 32 seconds. Because each decimal point is 1/10 of 1 minute, and 1 minute is 1,852 meters, 1 decimal is equal to 185.2 meters. So in other words, that there, if we went to 53.6, that would be a difference of 185 meters. Now that's fine for navigation in the air, because 185 meters, you'll pass over that very quickly if you're flying. So there's no real requirement to have seconds, unless you're specifically looking for a accuracy. Maybe you're doing some survey, maybe you have to pick up something. But 0.5, or decimalizing the minutes here, is more than adequate for a navigation within with aviation. Now in flight plans, you actually don't even use a decimal. You just use the first 4 digits of the latitude and 5 digits of the longitude. So that was latitude and longitude. There's another way of using coordinates, and that's called the Universal Transverse Mercator projection, and its coordinate system used in that projection. A variation or a derivative of that is the military grid referencing system. So most topo maps will use the military grid referencing system, which is, as I said, a derivative of the UTM. What's the UTM? How does that use? Well, the UTM system uses meters for the basic measurement and divides the world into 60 zones of 6 degrees width, where latitude and longitude used nautical miles, and the world divided up into 360 degrees and then subdividing that into 60 minutes and 60 seconds. The UTM system uses meters, and it does that by, as I said, dividing the world up into 60 zones, each of 6 degrees width. Each zone is then divided into meters. And so when you look at the coordinate system for UTM, it would look something like this. This here is a UTM band, and here are the meters representative of a coordinate within the UTM system. So it looks a little bit complicated, but it really isn't, and I'll explain it on the next couple of slides. So in full, here is the UTM coordinate. So this is the zone number, and here is either a hemisphere or a row letter. Now that can actually raise a bit of confusion, because if you're using the hemisphere, it'll either say N or S for north or south. But there are rows used in the UTM system, and they are lettered from A through to X. So N could actually mean a row as opposed to the hemisphere. So sometimes that's an area of confusion. You need to be very careful in using that. But for what we do, it's very rare that we'd actually ever use this. Here are the meters east, and here are the meters north. Now, quick tip for you: if you need to use these UTMs, UTM coordinates, the easiest way to get a six-figure grid reference, and most people would be familiar with six-figure grid references, is to count from the right to the left 5 places. 1, 2, 3, 4, 5, and then use that as your first number. So a six-figure grid reference here would be 666, the number of the beast. And then 1, 2, 3, 4, 5, using these 3 numbers here, 888. Well, this example really doesn't help because 666, 888 doesn't really show you anything, but I'll show you on the next slides. Here are those UTM grid zone numbers. As I said, actually I made a mistake before. It actually starts at C and goes through to X, and the reason for that is A and B are actually used, but these zones are very, very narrow in the polar areas, and they cover the Antarctic continent. What they're mainly concerned with these zones is actually land masses where people are. So it goes from C through to X, but it does not use I and it does not use O because they can be confused with 1 and 0. So C through X, omitting I and O. And each of them are numbered from 01 through to 60. Remember that there are 6-degree bands. Now let's have a look in Australia. If we are in, say, southern New South Wales, we are in band 55, zone hotel. So 55H. If I was in, say, North Queensland, I would be in 55 kilo. If I was in Brisbane, I would be in 56 Juliet. That's important to know when we're using topo maps. Here is a close-up of the UTM grid zone numbers for Australia, but there is a mistake with this, and can you spot it? Yep, it's pretty obvious. I used I here. I got this off the net, and that's a mistake. It should go G, H, J, K, L, M. And as I said before, J, if you're in Brisbane, you'd be using J. If you're in southern New South Wales, you're using H, and you're in zone 55. Now that's a UTM system. The military actually came up with a variation on the UTM system, and it's called the Military Grid Referencing System, and it's the one that we're most familiar with. What they do is they divide the UTM zones up into squares of 100 kilometers by 100 kilometers, or 100,000 meters by 100,000 meters, and then they give each square a 2-letter designator. This is the most common means of coordinate systems on a topographical map. Now the important thing is that in MGRS you must use both the grid zone designator and the 100 kilometer square designator, and if you can't do that you have to at least use the map title. Let's have a look at why. Okay, here are a couple of grid zones. This is 02 November and 03 November. As you can see in here, these are the 100 kilometer by 100 kilometer squares, and each one is given a designator. Kilo Papa, Lima Papa, Mike Papa, November Papa, etc. Now down the bottom of this map, you can see those UTM coordinates given there and there. Remember what I said to you before about figuring out which numbers to use, counting 5 in from the right, 1, 2, 3, 4, 5, and that's where you start. These first 2 numbers of the 5-digit section are the grid numbers that you would expect to find on a topo map. Also notice on this map here you have latitude and longitude. We'll talk a bit about that later on, but there's some good information on this. All you need is to understand where they come from. So here we have the eastings of the UTM system. 478000 means we're 478,000 meters east. That's what it would seem. There is a bit of a difference to that. We actually start each zone in the middle of the zone at the 500,000 meter mark. So in actual fact, we are, 22,000 meters west of the middle of the zone, but we only use those numbers there to mark the grids, and then when we do a 6-figure grid reference we divide each grid up into tenths. So that point right there would be roughly 775, 77, and then 5/10 across. So here in this Marginalia, we see some information that we can use. First of all, there's the grid zone designator, 56 Juliet, and the 100 kilometer squared identification is Mike on the left 2/3 of the map and November Mike on the right 2/3. You'll be able to figure out which one's which, because the grid numbers will go up to 96, 97, 98, 99, then I'll go to 00 and start again, and you'll be able to figure out this is November Mike. Now over here in this example, it's shown that the sample reference is Mike 886157. The full six-figure grid reference would be 56 Juliet Mike 886157. Of course, if you're talking to someone and you know that they're in your area and you know that they're going to be in your same grid zone as you and 100 kilometer square, you know that they're working off the same map, then normally you just give them the six-figure grid reference. But to ensure that the information gets across to say, ops center or control or the chain of command, the full grid zone designator and 100 kilometer square identification number should be included in any grid reference. So now we've seen two different coordinate systems, the latitude and longitude using degrees, minutes and decimal minutes, and then the UTM system and the MGRS system. Which one do we use? Well, aviation always uses latitude and longitude, because provided it has the numbers there and it says either north or south or east or west, you're never going to have any confusion. Don't have to worry about grid zone designators or anything like that. So it doesn't require any designators. However, most emergency services will use the MGRS system, which unfortunately is useless to a pilot unless he or she can convert it into a latitude and longitude. Now that's doable, GPSs can do that, but it does take a number of keystrokes. So you don't really want to provide that sort of information to a pilot in flight, because it just increases their workload. A GPS can convert it for you, or you can get an app for your iPhone, iPad, Android device, and it'll do it for you. Here's an example of the use of degrees, minutes and seconds, degrees, minutes and decimal minutes, UTM and MGRS for exactly the same point, which is the windsock at the airfield at Taree. So here you can see right down to 32 degrees, and remember each one of these is 1,852 meters, and this is 1/60th of that, so each one of those is about 30 meters. So if I went 152 degrees, 30 minutes, 33 seconds, well, I know that's going to be 30 meters further to the east of this coordinate here. In aviation, we use degrees, minutes and decimals. Here you can see it's decimal 3 places, actually usually only 2 decimal 1 place. Here is the UTM version of the same area, 56 Juliet, and then we have the series of numbers after it denoting east and well, it's actually north, but it's only because they start from the south and head north towards the equator in the southern hemisphere. And here's the military version of exactly the same thing. It uses the same grid zone designator, but it uses the Mike Kilo as the 100 kilometer square designator, and by using that you can dispense with that number there and those two numbers there. So that is a 10-figure grid reference for that point there, which will get you down to 100 meters, 10 meters, and then down to 1 meter. So that will get you to an accuracy of 1 meter, 10-figure grid reference. Let's now look at Map Legend and Marginalia. Now the Map Legend can provide you with lots of great information. And the Marginalia is all the information in the map's margin, which includes that legend and any survey information. So things to check when you're looking at a map. Well, first of all, you should be checking the magnetic variation, and for the most part, if you've been using maps for a couple of years, you'll know what it is in your local area. It only changes by a small percentage of a degree each year. You'll be looking for the map edition and recency of the map. That will be something of importance to you. The datum used, if you're that way inclined, if you're a bit of a geek. Any legend information such as grid zone designators, and the location of key places. So let's look at the map edition and recency. So aeronautical charts are updated at regular intervals, and it's a legal requirement for an aviator to carry current charts in his cockpit. But what with the electronic flight bags and smart devices now, I think that legal requirement is going to be reviewed. Topo maps, obviously they can vary in their accuracy between editions, and if you're looking for cadastral information or information about buildings and their locations or built up areas, you might find that your map could be up to 20 years old, if not older, and so what you see on the ground isn't necessarily reflected on the map. And that's what I just said there. Cultural or man-made features can change significantly between editions. So looking at the topo maps in the ACT area, you can see here are all the different map editions. Where are we? Here we go. Map edition. So there's Wagga. So Wagga 8327. That's the serial number of that particular map. And then to the north of that, it's 8328. That's Coolumine. And there, Bar Medman 8329, etc. and so forth. So if you can't get the grid zone designator, at least give the map edition or map number to ensure that you don't provide a grid coordinate that could be confused. The datum. Well, datum, which is singular for information, is a reference survey, and it can differ between global regions. We use a datum as a reference point from which the coordinates are measured. So the WGS 84, the World Geodetic Survey of 1984, is used by the GPS system. So if you're going to be programming your GPS, make sure it's in WGS 84. In Australia, the Australian datum is GDA 94. So if you're a surveyor and you're in Australia and you want your survey to be accurate, you'll be using GDA 94. But for us, we're going to be using GPSs, so WGS 84 is fine for our sort of operations, unless of course you're a surveyor. The Australian previous datum was the Australian Geodetic Datum 66, which was, guess when? 1966. It was updated in 1984, but the current one is the GDA 94. If there is a difference between the old system and new system that's of interest to us, is that 200-meter discrepancy can occur. In the Marginalia, they'll tell you how to convert, but for the most part, we don't have to worry too much about it. So here is the information that you'll find in the Marginalia about the datum. So looking over here, to convert from the World Geodetic System 72 to the Australian Geodetic Datum in 66, you need to increase values, etc., by 172 meters. So there's that inaccuracy. Here is the grid zone designator and the 100,000 meter square identification. Here's a bit of information telling you to ignore all the other numbers except for the large number on the in the margins, and that's the grid line number that we're concerned about. Here's a reminder on how to do a grid reference, and here is a reminder on how to present that grid reference. And then here it says, before giving a grid reference, civilian users should state the number and name of this map. So there is that map number and its edition version, and there is that grid reference. So there's two ways to show it. There's MGRS without the grid zone designator, MGRS with the grid zone designator, and this the six-figure grid reference using the map edition. Some more information. Tells you what the scale of the map is, 1 to 25,000. Tells you what the contour interval is, 10 meters. Tells you a bit of information about how the grid is done. That's only for the geeks amongst us. When the aerial photography was obtained, when the field revision was, and when it was printed. So there's 5 years between aerial photography and printing. It also tells you that sometimes the roads won't necessarily be depicted, the depiction on the map won't necessarily reflect what you actually see on the ground. So the legend provides all the decodes or the symbology that you'll see on the map, and different types of maps will give you different symbology, even between topo maps. And in part 1 we saw that difference in the map to the north of Wagga. looking at the symbology will give you some good information that you can apply to getting situational awareness. So think about this. Consider the operation you're doing. It could be support to the emergency services, it could be fire, you could be helping out with evacuations, you could be doing a survey, you could come across a vehicle accident, there could be any number of different scenarios. If you've already done a map recce, you can have a look at things like where's the schools, police stations, hospitals, fire stations, SES, ambulance, etc. If you're concerned about navigation, well, there you go. There's a pipeline, easy to see above ground, but here it goes underground, so you may not necessarily easily see it. You may see some disturbed earth or evidence of it from the surface, but then you may not at all. Topo maps, sometimes topo maps show power lines differently to aeronautical charts. Trig stations showing you high ground. A trig station will usually you'll be able to see some sort of marker on top of the high ground. Landmark area, ruins, cemeteries, quarries, silos, mines and helipads, all good information. If you're supporting firefighting, well then blue features are interesting for the pilots because that's where you can get water to bomb the fires. On an aeronautical chart, the information of use for navigating through the air. Obstructions, or a group of obstructions, beacons, broadcasting stations, combination of the two, a broadcasting station with a lit mast, and a broadcasting station with a mast over 300 feet high. I'm not going to go into details of why that's important, but here it tells you the numerals in italics indicate elevation above sea level. The height above ground is shown in upright type within the parentheses. So 507 is the elevation of the top of that mast above sea level, and the actual height of the mast from the foot to the top is 330 feet. Here's power lines and an isogonal. Here is a legend on another topo map. Primary road, in this case here, it's a large thick red line. Secondary and other roads are thinner red lines. Railways are depicted thus. Abandoned railways are depicted thus. And here is a power line, a telegraph or a telephone line, that is shown thus, which is different to other topo maps. Elevations, if they're in brackets, it's calculated. If it's not in brackets, it's measured. Other indicators of some of the features we saw in the previous slides. Contour lines, escarpments, cliffs and bluffs, etc. Let's talk about the concept of north. These days, by convention, north is at the top of the map. So facing north, the sun should be rising to our right. Back in the old days, that wasn't the case, and you had maps that were depicted in various ways, with some of them with Jerusalem as the center of the map, obviously for those medieval maps. But the north for us is important for a couple of reasons. Well, first of all, magnets, the magnetic north pole will be where our compass will be pointing to, and lines of magnetic flux will emanate from the north magnetic pole, and they'll cause a variation in what the compass says. So the compass magnetic north compared to what we see on the map, which will be grid north, and that's even slightly different to true north, but that's not important for us, the difference between true north and grid north for the most part. And this variation can actually differ in various parts around the world and can be either east or west, and it's also constantly moving. Now, lines of constant variation, constant magnetic variation, are called isogonals. And lines where there are no variation are called agonic or agonic lines. Here is a diagram of the various isogonals from around the world, the lines of constant or constant magnetic variation. Let's have a look at what, in fact, before we go on, down here is the south magnetic pole. You can see all the lines of magnetic flux emanating from here, which is due south of Australia, but not on the actual geographic magnetic pole. Up here is the north magnetic pole, which is just to the north of Canada. And again, it's not exactly on the north geographic pole. Now within the Australian area, this is what we have. We have line of magnetic, constant magnetic variation of 10 degrees east passing through this part of Eastern Australia. So in, say, New South Wales, we're looking at about 12 or 13 degrees east would be our magnetic variation. In Queensland, from where I'm from, is about 8 degrees. So you need to extrapolate when you have a look at a diagram like this, or if you might remember on that whack I showed you of Perth, we had 2 degrees west. So have a look at the Perth area there. You can see that, yeah, that's roughly 2 degrees west of the Agonic line. The Agonic line passes roughly through Kalgoorlie. So variation is east in this part of Australia and west in this part of Australia. This diagram here depicts the difference between grid north, what's on the map, and true north, towards the true geographic north, and where the compass will point, magnetic north. Now the difference between the grid north and magnetic north is 11.8 degrees east in this area. Have a look down here as well. So this is true for the center of the map. Magnetic north is correct for 1980 and moves easterly by 0.1 of a degree in approximately 3 years. So if you have a 30-year-old map, you could actually have a difference of 1 degree. For our operations, that doesn't really mean too much, but if you're a surveyor, that means a lot. Now let's have a look at what that means to us when we're doing our navigating. Let's say I wanted to walk due east on a heading of 090, or sorry, a track of 090. So here's my track, due east 090. If I look on the map, there would be my grid north as depicted on the grid lines on the map, and I would draw my line 090. So the difference between that, the angular difference between that line and that line is 90 degrees. So the grid bearing would be 090. Now I take out my compass so I know that I'm traveling in the right direction, and I look to see where north is, and my compass points in that direction there. The problem is where the compass is pointing to the north is different to what the map says, and it's different by, in this case here, 11 degrees, which means that if I'm going to be using my compass to follow my track, I need to apply that variation. Now the compass points slightly to the east, which means that the track that I need to follow is actually going to be an angular distance slightly less than that 90 degrees that I measured on the map. And in this case here, it'll be 90 minus 11, or 79 degrees. So if I'm using my compass, I would be walking along a bearing of 079 degrees to ensure that I am heading along a track of 090 degrees as depicted on the map. So the important thing to remember there is magnetic north rules the compass, grid north rules the map. So as we are using our compass, it's pointing to magnetic north, not grid north. And when I'm using my map, the north on the map is actually grid north. Now if you have done orienteering or navigation or things like that in the past, and you're from, say, the eastern area of Australia, you may have heard the mnemonics GMS or MGA, GMS Grandma Sucks, or MGA My Great Aunt. Well, they stand for Grid to Magnetic Subtract, GMS, Grid to Magnetic Subtract, or MGA, Magnetic to Grid Add. Now that works fine if you've got a variation that's east, but it doesn't work fine if you're over where it's west, where you need to do the opposite. And so within aviation, they've come up with a different saying, and this is it. Variation east, magnetic least. Variation west, magnetic best. And all that means is if you are in the east and if your variation is to the east, like in this diagram here where our magnetic variation is 11 degrees east, then the magnetic bearing or track that you want is going to have to be subtracted from the true or the grid north. So here we saw that where we want to go on the compass, which is east, we would need to be heading along 079, which is the variation east subtracted in order to give the magnetic. So variation east, subtract the variation in order to get the magnetic. Variation east and magnetic east. And if you are west of the agonic line, so you're over in Perth, when the variation is west, well then you add the difference between magnetic north and the grid north. That's the end of part 2. I hope you enjoyed that. Part 3 and part 4 are coming up soon, so I'll see you then. Bye bye.